Hi, today we're going to go through the 2009 PAT paper looking at the second lot of multiple choice questions, questions 18 through 22. So in question 18, we're told a time of flight mass spectrometer can be used to determine the mass of charged molecules through the equation given here, where T is the time of flight, D is the distance, the length of the tube, so 1.5 meters, M is the mass of the molecule, Q its charge, and U is a 16 kilovolt accelerating voltage. We're told if we are considering a single elementary charge here, 1.6 times 10 to the minus 19 coulombs, what is the associated mass for a time t of 30 microseconds? Well, it's simply a matter of rearranging a formula. So if we square both sides of the equation, we get t squared is d squared into m over 2qu, which tells us that, in fact, m is equal to 2t squared qu over d squared, which is equal to 2 times 30 times 10 to the minus 6 squared times 1.6 times 10 to the minus 19 times u, 16 times 10 to the 3, divided by d squared, 1.5 squared. Well, that's equal to 2 times 900 times 10 to the minus 12 times 1.6 times 10 to the minus 19 times 1.6 times 10 to the 4 over 3 over 2 squared is 9 over 4, which is 2.25. So let's just cancel off this for approximation purposes. So this is approximately equal to 900 times 10 to the minus 12. 16 squared is 196, so that's 1.96 times 10 to the minus 19 plus 4 minus 15, which is going to give us approximately 1.9. Let's do 9 times 2, so that's 1,800 times 10 to the minus 27, which is approximately equal to 2 times 10 to the minus 24 kilograms. So that's D. So question 19 tells us that a object travelling at a high velocity in a fluid experiences a drag force F equals k v squared a for velocity v and area a. Now I ask, what sort of quantity is k? Well, what we're going to do is we're going to do something called dimensional analysis. And if you haven't seen our video on this already, I recommend you watching, because we go thoroughly into explaining how you do it. And it'd be very useful to do that before you watch the solution to this video. What we're going to do is we're going to find, using dimensional analysis, the dimensions of k, and then from that deduce what type of quantity it is. So as we said before in our video, dimensional analysis is breaking things down into 3 fundamentals: length, mass, and time. For our case, it's length, mass, and time. There are only 3 things we're concerned with. So what we're going to do is we're going to write this as k is F over v squared a. And we're going to break down each of these 3 into their fundamentals. So force, what is force? Well, force is mass times acceleration. So mass obviously has a unit of mass, and then acceleration has length time to the minus 2, as we know. V, well, that's distance over time, so that's length per time. And area, well, that's distance squared, so that's length squared. So that means what we use a square bracket notation to notate the dimensions. So the dimensions of k are, well, the dimensions of force are mass, length, time to the minus 2, over, well, v squared, so that's L squared t to the minus 2, and then a, L squared. Well, that's equal to mL t to the minus 2 over L to the 4 t to the minus 2. So these cancel. This cancels, sending that to a 3. And that gives us that the dimensions of k are equal to mass and length to the minus 3. So that's mass per volume. And what do we know is mass per unit volume? Density. So the answer to this question is, it is D, density. So in question 20, we're told that a battery is connected in a series across 2 identical resistors in series, and one resistor is instantaneously replaced by an uncharged capacitor. Now ask, what happens to the current when this resistor is replaced by an uncharged capacitor? Okay, well we know that current is voltage over resistance. And we're not replacing the battery, so the voltage is a constant. So our voltage in this circuit does not change when we replace the battery with the resistor with the capacitor. What about the resistance? Well, when a capacitor is uncharged, it has a very low resistance. So when you instantly replace the resistor with a capacitor, the actual resistance of the circuit drops. So the current will rise originally, because we see that the bottom of this equation here falls, so the current increases. So initially, it will rise. But as the current goes round, the charge will build up on the capacitor, and they'll build up and build up and build up, they'll build up at opposite charges, and that will increase the resistance in the circuit. So as the current flows, the resistance rises, and it increases exponentially. So eventually the resistance will increase beyond what it was before. So the resistance will up and up and up and up, so the current goes down, down, down. So the answer to the question is it will initially rise, then fall. So in question 21, we're told that a light beam like this travels towards a prism, a glass prism, and asked what happens to the light beam as it strikes the prism. Well, we just go through our fundamentals of refraction. So we know we always draw a normal to the surface, like this, and we measure all angles relative to the normal. And we know that in a material of higher refractive index than the one it's coming from, so something refracts from something of low index to high index, the light will refract towards the normal. So what that means is, as it's striking like this, in fact this line probably isn't the best. Let's draw another ray of light first. We're going to strike like this, and let's draw the normal relative to that line of instance. So it strikes like this at some angle theta. And well, what could happen is two things. One is it would refract upwards, it would refract away from the normal. But we've just said that the prism is glass, and so it has a higher refractive index than the air. So that means it's going to refract towards the normal, like this, at a new angle phi. And that angle phi will be less than the angle theta, which means it's going to be an answer of B. It is bent down. So question 22 says that the moon orbits at 400,000 kilometers. It orbits the Earth at 400,000 kilometers with a period of 2.4 times 10 to the 6 seconds. I'm asked, what is the acceleration toward the Earth? Well, the way we do this is we assume, as always, a circular orbit. And when we assume a circular orbit, as we know from our separate video on orbits, which I would recommend you watch, that the centripetal force will be equal to the gravitational attraction from the Earth. So the net force on the object, ma, that will be the net force, will be equal to some centripetal force, mv squared of r. So it's going to be, obviously, in a spherical orbit, so it has to have a centripetal force that will cause its acceleration. Okay, so we can get rid of the mass and get that a is equal to v squared over r. But we don't have anything to do with v. We have r, we don't have v. So what do we know about v? Well, v is actually equal to omega r, where omega is our angular velocity. And that simplifies to omega squared r. But what's omega? Well, we know omega is in fact equal to 2 pi over t. Omega is the angular speed, so you do the angular distance, 2 pi, over the time period, t. So 2 pi over t. So that means a is actually equal to 4 pi squared over t squared times r. Okay, well that's equal to 4 pi squared times 400,000 times 10 to the 3 divided by time period squared. So that's 2.4 times 10 to the 6 squared, 2.4 times 10 to the 6 squared. Okay, well that's approximately equal to, well, pi squared is approximately 9, times 4 is 36, so that's approximately 40. So it's about 40 times 400,000 times 10 to the 3. So it's approximately equal to 40 times 4 times 10 to the 8 divided by 2.4 squared. So we'll write that as 2.4 squared times 10 to the 12. Well, that's equal to 160 times 10 to the 8, or 1.6 times 10 to the 10, divided by 2.4 squared times 10 to the 12, which is equal to 1.6 over 2.4 squared times 10 to the minus 2. And, well, we know this is going to be roughly of magnitude 10 to the minus 2, and there's only one 10 to the minus 2 or 10 to the minus 3 when you divide this by this. So we know it's going to be in the region of 10 to the minus 3, so that gives us the answer of A.